Right, I know. The next class is a week from today. But then I think from that point on, we'll have regular classes. That's between you and the TA, but I think you've had more than a week to do it, so it would be a good idea to do it early, just hand it in early in the day. Typically, when things are on paper, they're due physically in class, so it should be something close to that. If you're emailing it to your TA. Are there any scientific questions about the material in the course? Okay, so we were talking about modeling, and we said before we can talk about control, we need to be able to describe what we're controlling. And what that means is we need to first figure out how to do modeling. So we went through sort of the general formulation of how to do modeling. And we said the most general way of thinking of doing modeling is to first identify your goals, and that tells you what type of model you need, at what level of detail you need. Once you identify your goals, then you move on to formulating a model. All I did is copy this over from over there. So I have it on the left side of the board. The first thing is you want to identify the variables. So are they molecular variables? Are they macroscopic variables? And you divide them in. There are certain variables that you would like to be in certain ranges, and there are certain variables that you can directly manipulate. So you want to separate the control variables from the manipulating variables. And then, of course, you would do your simplifying assumptions, and we'll talk about those in an example. And then once you have your simplifying assumptions, you formulate your equations for that correspond to the simplified assumptions. Then what you do is once you have your equations, hopefully you can solve the model. You either solve it analytically. You would love to solve it analytically, because when you have an analytic solution, you can see immediately how all the parameters affect the solution by where they sit in the equations. On the other hand, sometimes it's too hard to solve them analytically, so then you have to do it numerically. When you solve a model set of equations numerically, it's not so obvious what the individual parameters do. What you usually have to do is solve it for many different sets of parameters. So an analytic solution is better, but if you can't do it, then you can deal with the numerical solution. Once you've carried it out, then you're not done. You need to validate the solution. That is, who said the assumptions that you made were actually apply in real life? I assume the moon is made out of green cheese. Well, everything that follows from that may be logical, but if I check the answer, the moon is not made out of green cheese. So it's possible that my assumptions were not valid. So I have to validate the model by comparison with experimental data. And if it works, great, I'm happy. If not, then I have to go back and maybe change my simplifying assumptions and change my equations. So that's sort of the basic outline. And we're looking at a simple example here where we take a tank where we have fluid going in, this thing, that wasn't supposed to bang into it. Okay, so here we have a tank with no reaction in it, and we have a certain concentration of A coming in and T less than 0. And since there's no reaction, Ca coming out is the same as Ca going in because there's no reaction. And at time t is equal to 0, there's a step change in Ca to some other value. And we'd like to see what the response is at the output. Now, we're assuming that whatever is in the tank is well mixed. And we discussed what that means last time, that the mixing is fast. And the things we can manipulate in this case are Va in and Ca in. But we observe Ca out and V out, where little v is the volumetric flow rate, little v is in units of length cubed per unit time, and Ca is in units of moles per unit length cubed. And so we made some assumptions. We assumed that, so we went through and we identified our variables. Then we made some assumptions. Our assumptions were that for t less than 0, before I do my step change, everything's at steady state. So in particular, well, it's at steady state, so the volume of the system doesn't change. It's full. Yeah, I didn't have to assume that, but I didn't have to have a system like that, but I did assume that. Or if you like, you're given that, so that the V is fixed. So in order for this to hold, this has to hold. Then we also assume, again, this well mixing. We spoke about that last time. And we also assume that the density is uniform and constant. So even though Ca changes, the density, the number of moles per liter, doesn't change. So the concentration may change, but the moles per liter doesn't change. So we made those assumptions. And then what we would like to do is go to the next step. We would like to formulate some equations. So are there any questions so far? All right, so if we want to formulate some equations, let's just do some for reference. If the volume of the system were changing, which is not here, but just for fun, let's remember that. If the volume were changing, then I would need to do a mass balance on of the total mass. I would need a total mass balance. So let's let rho be the density in, if you like, units of mass per unit volume, or length cubed. And again, I'm going to let, V be the volume in units of length cubed, and little v be the volumetric flow rate in units of length cubed per unit time. Just so we're clear on the units. And if I were doing a mass balance, a total mass balance, I would have, say, that ddt of the total mass. The total mass is rho times the volume, because rho is mass per unit volume times the volume is mass. And that's equal to in minus out. And there's no reaction. So there's no reaction. Mass is neither, well, even if there were, mass is neither created nor destroyed as long as we stay away from relativity. So the in is the volumetric flow rate in, and out is the volumetric flow rate out. And if V in and V out are the same, well, that is going to make things quite simple. But I want the mass in and the mass out. So that's rho V in, rho V out. And there I would have a situation that if rho is uniform and constant, if rho is uniform and constant, which is something we assume that the density is uniform and constant, then I can pull rho out of the derivative here. The rho's cancel, and I just get dv dt. And that's the only variable, so it becomes time dependent. There's only one variable, so it becomes a total derivative. It's just v in minus v out. So this would be a mass balance on the total mass. Now, in our particular problem, I assume that the volume is fixed. So in this particular problem, dv dt is 0, so v in equals v out. But you can imagine that if I start with an empty tank, then dv dt is not 0 until it fills up. But that's not the case here. That's just for reference. Now, let's talk now about, if we want to do a species balance. On species A. So if you notice, here species A is what's coming in and what's going in. So we're going to use the general equation of chemical engineering. Anyone want to take a guess at what the general equation of chemical engineering is? If you can distill all of chemical engineering into one equation, what do you think that equation would be? is equal to accumulation. Oh, you said I couldn't make that? Yeah. So the general equation of chemical engineering is the rate of accumulation is equal to the rate in minus the rate out plus the net rate, or the rate of generation minus the rate of consumption. So in our problem here, in this problem, there's no reaction. So there's no consumption and no generation. But the rate of accumulation of species A. So species A is CA, is, remember CA, let's just write the units. CA has units of moles A per unit volume. So if I multiply by the volume, I have moles of A, and I take ddt of this. And that's equal to the rate of A in. Well, the rate in is CA in times V in. Again, moles A per unit volume, volume per unit time is moles per unit time. Every equation, every term in the same equation has the same units. Moles A per unit volume times volume is moles A per unit time. Moles per unit volume, volume per unit time is moles per unit time, A per unit time. Minus CA out, V out. So, and that's fine. So n plus 0, there's no generation or consumption. Okay, well, let's notice what we said is that V is fixed and that the density is uniform and constant. If V is fixed, then V comes out. Since V is fixed, V comes out. And since the density is uniform and constant, these are equal because density doesn't change. Or we could actually just see it from here. Since the volume doesn't change and the density is uniform and constant, this is 0, so V in equals V out. So then I can just drop the superscript and just call them V. So what do I have left? I have dCA dt. And again, since time is the only variable, because I've assumed it's well mixed, space is not a variable. So then I could turn the partial derivative into a total derivative because time is the only independent variable. So I have dCA dt. And I'm going to divide through by the volume. Is equal to CA in minus CA out times, or I'm going to divide by the volume over the volumetric flow. So I did a couple of steps of algebra there. Hopefully that wasn't too quick. I factored out the V, and I put it in the denominator of the denominator. So being in the numerator or the denominator of the denominator is the same thing. And I divided by V, big V. And this thing here, V over little v, let's see what the units of that are. The top, big V, has units of length cubed. And the denominator, little v, has units of length cubed per unit time. So notice the overall units of this thing are units of time. Unequal units. This is units of time. It's the volume of the volumetric flow rate, and since it is units of time, we'll use a Greek letter tau to represent time, units of time. And this tau, which you'll see in your reaction engineering class, let's see what it is physically before we give it a name. If we think we have the volume of the reactor divided by the volumetric flow rate of the fluid going in and out, because it's constant density. So what that's telling me is how long it takes to replace all the fluid in the reactor. And in fact, that's a big issue these days with COVID and why that machine was inadequate, well, especially since it's not plugged in. But they always talk about air exchanges. So if you want to worry about aerosols, you want to make sure you clear out the air here how many times an hour. And usually they say at least 6 times an hour is healthy for in COVID times. Well, that's just 1 over this, 1 over tau. It's how long it takes to clear out the, how many air exchanges per hour. You take the inverse of that, that's this thing, the volume over the volumetric flow rate. And this is called the space-time. It has nothing to do with relativity. It's called space-time because it's the time it takes to replace the whole space of the reactor. It's an unfortunate term because that's a term that's used in relativity. It has nothing to do with relativity. And it characterizes the reactor. It has nothing to do with reactions. So I can write this as Ca in minus Ca out over tau. And notice again, both sides have units of concentration per unit volume time, moles A per unit volume time. Moles A per unit volume time. Has to be that. Yep.
So is space-time the same thing as reference time?
I'm sorry, I can't hear
Is
you.
space-time the same thing as reference time?
Good. That's actually a very good question. It has a little bit of a subtlety to it. If the density is uniform and constant, then the answer is it's equal to the average resonance time. Now, if the system were not well mixed, different particles could have different resonance times. Because the system is well mixed, the average resonance time equals the space-time. However, if you have a non-constant density system, it's more subtle. For example, if the system expands if you have a reaction and it expands with reaction, then it speeds up. And the question is, how do I define tau? Usually I'll define it by the volumetric flow rate that comes into the reactor. But the volumetric flow rate going out, if the system expands upon reaction, is a lot faster. So then the space-time based on the inlet volumetric flow rate is not the same as the average resonance time. That may be more than you wanted to know, but that's the, but you asked the question, I want to give you a good answer. And we'll get actually into non-constant density systems in a little while. So here we have our system, and let's notice what are the variables and what are the equations. Remember, we spoke about degrees of freedom. The degrees of freedom was the number of variables minus the number of equations. And usually for the problem to be well formulated, the number of equations and the number of variables should be the same. So let's see what the variables are. Well, if I knew nothing about the problem, all those assumptions, then my variables would be V out, Ca out, and actually the volume. So if I had a tank and I didn't tell you any of these assumptions, I'd tell you there's stuff going in and stuff going out. So you wouldn't know the volume because it could change with time. You wouldn't know the volumetric flow rate going out. I didn't tell you anything about it, and you wouldn't know the concentration going out. So there'd be 3 variables. Now, because of the assumptions, V is fixed, or from this equation, I know that V is constant. So that's one equation. Either the assumption that V is constant or getting it from here. The next thing was that the density is constant. That told me, since density doesn't change, that told me that V in and V out are the same. 2 equations. 3 variables, 2 equations. The third equation is this, the species balance. So I have 3 variables, 3 equations, I'm happy. Is that clear? Notice that 2 of the 3 equations I got just from the assumptions. So I didn't even have to, if I weren't being so pedantic now, I wouldn't have to write them down. I would have just written this down. But I'm trying to go through all the steps and emphasize them, which I won't keep doing all semester, but at least one time I want to do it that way. Is that clear? Okay, So now we need to solve this equation. And let me just notice, remember I said well mixed. I want to emphasize again what well mixed means. The well mixed not only means that the fluid everywhere here has the same concentration, but in particular the fluid in the effluent, which comes from here, is exactly the same as the fluid in the reactor. That's the main assumption of what a CSTR is. The fluid everywhere in here and outside that going out are exactly the same. So I don't have to write Ca out, because Ca out is the same thing as Ca in the reactor. So notice, I'm going to get rid of this out. I don't need it, because Ca out equals Ca, because it's a CSTR. So let's notice, and I'm just going to rewrite this equation. Right here, dCA dt. I'm going to move Ca as the variable. Ca in is a given. So I'm going to move this to the other side of the equation. Plus Ca over tau is equal to Ca in over tau. That's the equation I want to solve. And this is a linear equation because you don't have anything, CA's multiplied by each other with any power. Every term has precise either one CA or no CAs. So it's linear and it's first order because there's a first derivative. Does anyone remember how to solve a linear first order differential equation from your ordinary differential equations class? Anyone remember? Can someone yell? Yell. If you remember, just yell it out. A class where no one wants to yell? What kind of? Well, it's separated. All the CAs are on the left, and there's only one variable, dependent variable. Very good, the integrating factor. So I'm going to just derive the integrating factor here in general. If I have dy dt plus a of t y is equal to d of t. So let's just solve that in general. And we're going to refer to this, we're going to have so many equations this semester that are of that form, we're going to solve it once and for all. In this particular problem, a of t is a constant and b of t is a constant. But let's just solve it once and for all. So to solve it once and for all, I'm going to multiply both sides of the equation by e to the integral a of t prime dt prime t. It's a good thing I'm tall and reach the top of the blackboard. So if I do that, then I want you to notice that the left-hand side of the equation is d dt of e to the integral a of t prime dt prime y. And the right-hand side is b of t e to the integral to t a of t prime dt prime. That is, by multiplying by an integrating factor, I turn this into a total derivative. Let's just check. If I take a derivative of a product, so d dt of y times the integral, that's this times this, plus y times ddt of the exponential. Well, ddt of an exponential gives me the exponential back, times the derivative of what's in the exponent. The derivative, there were no t's in the exponent, there were only it's only in the limit. So the derivative is the integrand evaluated at the upper limit, which is exactly a of t. And the right-hand side is to multiply them together. Now since that's a total derivative, I can integrate. So now if I integrate, I multiply through by dt, and I integrate. And notice, t prime is not the same as t. T prime is green t, t is black t.
For the integrating factor, I see that the integration was from, it has like t up down, right? So what's the middle?
Right now, I'm going to leave it as just t. It could be, it depends on the problem, but it would be some constant. As long as it's a constant, it doesn't matter, because when I take the derivative with respect to t, the constant doesn't contribute. But good question. I like the questions. You're all asking very good questions. And there are often things that I could have said and should have said, but I only say them if you ask me. Okay, so if I multiply by tt and integrate, then, so I have d of e to the integral of t, a of t prime, dt prime, is equal to b of t, e to the integral of t, a of t prime, dt prime, dt. And now I integrate both sides. Now this is a total derivative, so I just get this thing at t0, so this thing, the curly bracket of t0, let's call it t1, and to the curly bracket of t2. I'm rewriting the curly bracket. And this thing is from t1 to t2. I'm not starting from 0 because sometimes I don't start from 0. I start from some t1. So I might as well write it in the general way. So this gives me e to the integral to t, a of t prime, dt prime, y of, and this is t2, y of t2, minus the same thing at t1. So I'll bring that to the other side of the equation. E to the integral t1, a of t prime, dt prime, times y of t1. Plus the integral t1 to t2, b of t, e to the integral of t, a of t prime, dt prime, dt. And now I'm going to multiply both sides of the equation by the e to the minuses. So I have y of t2 is equal to the integral, so I take e to the negative of this. E to the negative of this gives me e to the minus t1, t2, a of t prime, t prime, y of t1. So how did I do that? If I want to put a minus up here, then the t1 goes to the bottom. When I multiply by e to the minus this to both sides, I'll just keep the minus and t2 will be on the top. And then here I have e to the minus the integral to t2 of a of t prime dt prime. The integral t1 to t2, e of t, e to the integral of t, a of t prime dt prime. So this is the general solution. And I never need to derive again, it's right there. Let's look at the special case where a and b are constants, because that's what happens here. A and b were constants. So if a is a constant, then this just comes out of the integral, and I have y of t2 is equal to e to the minus a, it's just a constant, t2 minus t1 times y of t1. And what do I have here? So here I have plus. Well, if a is a constant, so here I have e to the minus a t2 minus something. Let's say this is whatever that. Actually, let's bring it inside the integral so I don't have to worry about that. If I bring this inside the integral, I bring it inside the integral, so I'm left with the integral t1 to t2, b of t, times e to the integral minus from t to t2, and actually I can pull the a out. I don't have to do the integral. I'm pulling a out. A is a constant, so I have a times t minus t2, t prime minus t2 times t2. And this just becomes t. That's that. And now what I can just do this integral. So let's do that integral. So this is the special case, a and b constants. So let's do the special case. Let's put it over here. So I have y of t2 is equal to y of t1 e to the minus a t2 minus t1. b is a constant, so b comes out. So I'm assuming b is a constant. And I can do this integral. So then I have b over a, because I take the integral of a times something. I can switch variables. If I change variables, I can let s be equal to t minus t1. So then this is ds, and this becomes e to the a s. So let's write it out. So over here, I've got, let's do it one step at a time. B times, and I'm letting s be t minus t1. So ds is dt is ds. And then the lower limit is t minus t1 is 0. And the upper limit is t2 minus t1. And now I need to see what I have here. So here I have e to the a. And I had a t minus t2. So t minus t2 is equal to t minus t1 minus t2 minus t1. So it's e to the s. So this is s minus t2 minus t1. I'm making this more complicated than it needs to be. I could have actually just done it directly from here, but let's see what we get. So here I have y of t2 is equal to y of t1, e to the minus a, t2 minus t1, plus b over a times let's see, times 1 over what's up there, b over a times the exponential, so the integral of the exponential gives me the exponential back of the 1 over a. So I get the 1 over a times the exponential. The exponential of the upper limit, s is t2 minus t1, is just 1. And the exponential of the lower limit is 0, 1 minus e to the minus a t2 minus t1. And that's the final solution. Sorry for making it more complicated than it needed to be, but I sort of went through all the steps doing it somewhat rigorously. Okay, so let's just review. We had a first order linear differential equation, which we solved by method of integrating factor. Here is the integrated factor in its most general form. When we did it in the most general form, we got this equation right here. When we specialized it to the case where a and b are constants, instead of being functions of t, it reduces to this form. And in this particular equation, a is equal to 1 over tau, and b is ca in over tau. And those are both constants, so I can appeal to that. Are there any questions about this derivation or about why we did it? Any questions about the derivation or why we did it? If somehow you got a little confused about having to change your variables here, you can always go back and just make a constant here and b a constant here and integrate it directly without going through this, and you'll get this much easier. And I just wanted to show that it was consistent, that if you go from the general form, it simplifies correctly. Okay, so why don't we plug in here? So y in this case is ca of b. So from this formula, I have ca of t2 is equal to ca of t1, y of t1, times e to the minus a. E to the minus a is 1 over tau, times t2 minus t1. t2 minus t1, plus b over a, Okay, what's B over A? B is this, A is this. B over A is just CA in. Times 1 minus e to the minus t2 minus t1 over 10. Any questions on that so far before we analyze it? Okay, so let's analyze it. Or let's do a little bit of manipulation. Let's rewrite this. Let's subtract CA of t1 from both sides. Because if you like, remember, in our situation, we had a CA, here we're letting T1 equal 0, and T2 be any time after that. So we know CA of T1. So let's subtract off CA of T1. If I subtract off CA of T1, then I'm going to get the exponential minus 1. And here I have 1 minus the exponential. So this will just give me CA in minus CA of T1 times 1 minus e to the minus T2 minus T1 over that. And I would like to be very specific here. CA in now, in this problem, what I mean is CA in for t greater than T1. This is the CA in I'm talking about. So this is, let's just be specific, this is CA in for t greater than T1. Because there were two CA ins, and the problem we're solving is for t greater than T1. Okay, there's a lot of math in this class, sorry, but you'll come to see that it's necessary. The first thing to notice is this is an exponential. And an exponential has a decay. It's an exponential decay. Yeah.
What is T2 and T1? Are those two separate?
T1 is when I introduce the step change, and T2 is any time after T1.
So is T1 0? Or is T1?
In this particular problem, T1 is 0. And T2 is any time after T1. Yeah. We want to make sure my notation is clear. If you have any doubt, make sure to ask. Okay, so this is an exponential decay. An exponential decay can decay really quickly or really slowly. What determines how fast it decays? The coefficient. And the coefficient here is 1 over tau, where tau is the space-time. So tau, remember, it tells me how long it takes to exchange the volume in the reactor. Obviously, if I exchange the volume in the reactor faster, I'll get to the new steady state faster. So that is the time constant that tells me how fast things are changing. This is no reaction. The only thing that reason it's changing is because of flow. So that's why tau is there. And let's note it. Let's plot this. Actually, I can plot it over here. I already started the plot. This is 1 minus an exponential. 1 minus, let's make this a little lower. 1 minus an exponential goes like this. Because as t2 goes to infinity, the exponential goes to 0, and CA in t2 just goes to CA in for t greater than T1. Where this value here, this value is the same as this value, because there's no reaction. That is, if I started out with CA1, CA in at this value coming into the reactor, well, I have the same value coming out. These are the same. If I do the step change, then eventually what comes out is going to be the same as what comes in, because there's no reaction. But instead of going as a step change like the input, the output is slower and goes as 1 minus an exponential. And let's just notice, I can write CA at T2 minus CA at T1 divided by CA in for t greater than T1 minus CA of T1. And that's equal to 1 minus e to the minus T2 minus T1 over tau. And as t goes to infinity, as T2 goes to infinity, this just goes to 1 when T2 goes to infinity. What does that mean? That tells me that as T2 goes to infinity, the CA1s are always the same. CA of T2 just becomes the inlet. The outlet equals the inlet. And we call this Kp. Kp, which is the steady state gain. The steady state gain is the variable of the output, y out of infinity, minus y out of T1, divided by y out of, divided by y in for t greater than T1, minus y out. So it's the change in the output over the change in the input. Why not just, instead of making it so general, let's just read it the way it was. So this is going to be, in this case, it's CA of T2 minus CA of infinity minus CA of T1 divided by CA in T greater than T1 minus CA of T1. So it's what comes out at infinity minus what came out at the beginning, divided by what goes in minus what was coming out at the beginning. And that's the steady state gain. And what you can see here is that the steady state gain is 1. That is, the change in the output is the same as the change in the input because there's no reaction. It's changing the output at infinity. And that's steady state is because it's at infinity. Are there any questions on that? Okay, well, the next thing to do is the validation. So, what I can compare this curve with the experiment. So, for example, I can calculate, let's say I want to calculate how long does it take for the output to reach 90% of its final value. So, question. How long does it take for CA, how long does it take? That is, what is T2? For CA of T2 minus CA of T1 to equal to 90% of CA in for T greater than T1 minus CA of T1. How long does that take? So let's look at it on this picture. I know that eventually the blue curve will go to the same limit as the white curve. How long does it take to get 90% there? So what is the T2 that will give me 90%? So I can calculate that from this expression that says when the numerator is 90% of the denominator. So when this is 0.9. So that tells me the exponential is 1 minus 0.9. So that says 0.9 is equal to 1 minus e to the minus T2 minus T1 over 10. So that tells me that 0.1 is equal to e to the T2 minus T1 over tau. Or when I take the log, I have a log of this, which is minus the log of n, is equal to T2 minus T1. And I have to multiply by tau. So I get tau is, let's see, I bring this to the other side of the equation. Yeah, I have e to the minus t2 minus t1. So I get t2 minus t1 is tau log n, which you can calculate. Yes?
Just when you're writing the exponential term e to the minus t2 minus t1, is that first minus sign apply to the whole fraction or just the t2?
Tell me which line you're talking about.
You can do it with times like.
Are you like here?
Yeah.
Yeah, it applies to the whole thing.
Okay.
I'm fussing a little bit with the t2 minus t1 because many times t1 won't be 0. In this particular problem, it's 0. t1 is 0.
Is T1 a variable or is it a constant?
T1 is the time that you choose to make your change. So for example, in this problem, I made the change at a time that I defined as 0. But let me give you an example why you want to keep the T1. You want to keep the T1 because you might have a CA in that looks like this. You might make two changes. So if I define this one as t is equal to 0, this is not t equals 0, it's t1. So if I want to look at what's going to happen after this change, I need to know how to do it relative to a value t1 that's different from 0. And I could have not just 2, I could have 20 changes. So that's why I'm fussing by keeping the t1.
What I guess what I'm asking is, if you're looking at this as a function, is a function of two variables or is it a function?
It's a function of t. Yes. So if you like, you know, we can fuss here, and we could say, I don't need the 2 here. I can just make that t. If you like to see a variable without a subscript. So there you have with, there's no subscript, so t is my variable. Before I called my variable t2. If you prefer, if you usual way of thinking is the subscript means it's a value as opposed to a variable, I got rid of the variable. I got rid of the subscript. So t is the variable. T is here, here, and here. But t1 is a fixed point in time. T1 is a fixed point in time. T is not. So is that more clear if I do it that way? Okay, I'm glad you pointed that out, because I want to do this in a way that's the least confusing.
How do you get ln of 10?
And I get the log of 10. Well, I have 0.1 is equal to this. So 0.1 is 1 over 10. So I have the log of 1 over 10 is equal to minus t2 minus t1 over tau. So this is log of 10 is minus log of 1/10 is minus the log of 10. And then I cancel the minus sign, and I multiply by tau. That's how I got this.
Thank you.
You're welcome. Any other questions? Okay, again, if you don't follow any part of the algebra, just ask me, and I'll help you go through it. All right, so let's just notice, now we need to do validation. Validation, that's what we're up to now. When we do validation, we compare with experiment. So here we make a prediction. Whatever log 10 is and whatever tau is, I multiply them together, and I can actually do the experiment by measuring the concentration in the reactor. I can, keep on taking little small aliquots out of the reactor and putting in the GC, and I can determine the time at which the concentration reaches there. If the concentration, the first thing I want to check is if I'm measuring the concentration as a function of time, does it even look like the curve? Is it the right shape of the curve? What do you think goes wrong if the shape is wrong? What do you think, which assumption that I made you think was bad if when I measure the output it doesn't look like this, it's a different shape? What do you think was the bad assumption?
Something wrong with that.
I can't hear you.
Something wrong with that.
No, the math, I didn't make any mistakes. You checked the math, but there are no mistakes.
I was thinking in terms of gravity based on that. That's why.
No, but the math is correct. So, the math is correct. But we made certain assumptions in the formulation. If the shape of the curve doesn't look like that, what do you think we did wrong? Well, you could measure the density. That's something that you can easily measure. So if I measure the density of the outlet and the inlet and they're the same, that's something I could suspect. But if I measure the outlet and the inlet density, they're the same, then I check that assumption.
What
well mixed. If the system is not well mixed, the curve won't look like this. Let's imagine I have a tank, and the mixing is so bad that nothing happens here, that the whole bottom doesn't get mixed at all, and what comes in goes straight to the outlet. It goes straight to the outlet, and this curve is going to rise almost immediately, because none of it's getting mixed. So if the shape is wrong, the well-mixed assumption is wrong. What if the shape is kind of right, but it just takes less time to get there? It rises, but actually, I always get calls when I'm teaching. Okay. So what happens if it just rises more quickly? It gets there, but it rises more quickly. But it looks like an exponential. Well, what happens then? If it rises almost instantaneously, then there's bypass. The inlet just goes right to the outlet. If it rises more slowly, but still like an exponential, then what that's telling me is maybe a portion of the reactor is dead space, but the rest of it's well mixed. So what happens there? If a portion of the reactor is dead space and the rest of it's well mixed, then the effective volume is smaller than I thought. So tau is smaller than I thought. If tau is smaller than I thought, then the time scale is faster than I thought, because it's smaller, so I get the result quicker. So that's what getting there faster means. What if I get there more slowly? I get there more slowly. If I get there more slowly, then that's a little more complicated, but that probably means that the fluid is sitting in the reactor, and instead of mixing, it's diffusing, where the diffusion is slow. So that's a possibility. And these are things you would have to check. Any questions on that? And that's the validation. So if my validation tells me, for example, that it's exponential, but I get there faster, then I have to change the assumption that the volume is the volume of the reactor, and that it's well mixed. If, on the other hand, it goes there almost instantaneously, then I've got a problem with my reactor. I better get a new mixer in there because it's not a CSTR. Okay, so now what I did so far, can someone take the pictures here of the, because I'm going to need to do some erasing while I answer a question. Do you take the pictures? Yeah. Because I'm going to need to do some erasing. Yes? I'm sorry, can I change the condition of?
Could you change the position of the inlet and outlet stream so that also help with the well mixing?
If I change, yeah, that can help with the, if I have the inlet too close, the outlet too close to the inlet, that can encourage it not to be well mixed. If I keep them further apart, that can encourage the mixing. And sometimes I may want to put baffles in. Baffles can work in both ways. They can make things mixed, but they can also separate it into different regions that don't mix with each other, but it can help them mix within a region. Other questions? Were you able to make many H's? Is equal to CA in minus CA over 10. That was the special case with no reaction. And constant density. And E phase. So that was a very special case. Now let's go through and do the more general case. So again, I've got accumulation is equal to in minus out plus generation minus consumption. And so the accumulation, we said, is dCAV dt, just as it was before. And the in is V in CA in, just like before. The out is V out CA out. And the generation and consumption is due to reaction. So I have an RA, which is the net rate of production of A. So RA is the net rate of production of species A per unit volume time. And it has units of moles A per unit length cubed time. So that's all the kinetic terms. So now, this has units of moles per unit volume times volume, which is moles A per unit time. Moles per unit volume, volume per unit time, moles A per unit time. Moles A per unit time. This is moles A per unit volume time. I have to multiply by volume. And I'm going to assume here that we're going to assume right now that V is fixed. So if V is fixed, I can take V out of the integral, out of the derivative, and I can divide by the volume. So I have dCA dt is equal to V in over V times CA in minus V out over V CA out plus RA.
Sorry, what did R stand for again?
Rate. R stands for the word rate. So here's the definition of R. No worries, no problem. Okay, now in this case, we've only assumed the volume is fixed. So we know V in, because that's what we put into the reactor. We know CA in, because we determine what goes in. We know the volume of the reactor. So these guys are known. But this guy is unknown, CA out. This guy is unknown, V out. We don't know those two. Because the reaction might cause a change in volume. For example, let's say I have A goes to 2B, and it's an ideal gas. I go 1 moles to 2 moles. It expands. So if it's expanding, it speeds up. Make sense? So what do? And I may have lots of species, not just A, I may have B, C, D, etc. So I need to, if the system is at constant, if the pressure and the temperature are constant, then the only way you change the density is due to reaction. If I have a reaction that doesn't conserve moles, it's certainly allowed. But at fixed pressure and temperature, the number of moles that fit in the reactor, is always the same. But the reaction changes the number of moles. So what that tells me is the total number of moles that fit in the reactor but it stays fixed even as the density of the mixture changes with reaction. So for example, e.g., A goes to 2B. So if I feed A in, I feed 1 mole per minute of A in. Well, 2 mole, and the reaction proceeds. So I have a mixture of A and B coming out. But B takes up a lot more room than A. So therefore, I have the density has got the mass density has gone down, even though the molar density is the same. But since the total number of moles that fits in the reactor is the same, by A turning into 2B, by the time it turns into 2B, it's traveling a lot faster because the volume of the reactor hasn't changed. So what does that tell me? That tells me that if I add up all the concentrations, so if I take the sum of all the concentrations of all the species. So this is over all the species. Where I labels the species as A1, A2, A3, all the species. And I multiply by V, I get the total number of moles in the reactor. And the total number of moles in the reactor doesn't change. So if I take the sum of the concentrations, that's moles per unit volume, multiply by the volume, I get the total moles in the reactor. So even though the CAs are changing with time, the total of the sum of the CAs times V doesn't change. And instead of writing these sums, I'm just going to introduce some notation. I'm going to we'll call this 1 dot C times V, because that's a lot nicer notation than the sums. So you can think of C as the vector, CA1, CA2, CA3, dot, 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 and 1 the vector of all ones. So if I take 1 dot, CA1, CA2, CA3, I just get CA1 plus CA2 plus CA3, etc. So is that clear? This is just a simpler notation, and it's just the sum of all the concentrations. And I know that d dt of n is 0. Since dn dt is 0, that tells me that v times d dt of 1 dot c is 0. And this is going to tell me what v out is, as we'll see in a second. So I have d dt of 1 dot c is 0. And we're going to derive the general equation for an unsteady, non-constant density CSTR. So what this says is I need to take 1 dot this equation. Because when I take 1 dot this equation, I get, so this is equation star. So let's take 1 dot star. What that means is I'm going to add up this equation for all the A's, for A1, A2, A3. So that gives me d of 1 dot c dt. That's on the left. And what that gives me is I have v in over v times 1 dot c in minus v out over v times 1 dot c out plus 1 dot r. So again, 1 dot means I add up for all the species. So here I add up the rate of production of A1 plus the rate of production of A2 plus the rate of production of A3, etc. Here I add up all the concentrations going out, which are the same as C's. I don't need DC out because it's a CSTR. C because it's a CSTR. And I know that, and this is a total derivative because it's a CSTR, there's no space variables. And I know that this is 0. I've just shown that that's 0. So what that tells me is I can now solve for V out over V. I can bring this to the other side of the equation, and I get V in over V, 1 dot C in, over 1 dot C, plus 1 dot R over 1 dot C. In other words, I didn't know what V out was. Remember, I didn't know what V out was. Now I know what V out is, because everything here is known. This is the input, the inlet concentration. This is V in. I know what they are. C was my unknown variable. It's still unknown. This, remember, is the same. This is just C, CA, because it's a CSTR, and it would be the out. R is the rate function. That already was here. That was unknown. It's still unknown. Divided by 1 dot C. So now I can plug into this equation, and I have dCA dt is equal to V in over V times CA in plus RA. And now I have CA times this whole thing. 1.R over 1.C plus V in over V, 1.C in over 1.C. Looks like a lot of notation. But what I've done is I've solved for what V out is. I know what V out is. Well, let's look at the special case of constant density to make sure we get the right answer. So let's look at this. I'm going to look at two special cases. So one special case constant density. In the constant density case, V out equals V in. So in the constant density case, it was the volume that is may exist. No, I think that's correct. Okay. So what happens in the constant density case? In the constant density case, the reaction doesn't change the number of moles. In the constant density case, the reaction conserves moles. Otherwise, I would change the density. So in the constant density case, if I sum up the rates of reaction, I always get 0 because the reactions conserve moles. So in that case, and moreover, the total number, 1.C is the total number of moles in the reactor times V. If the density doesn't change, then the total moles in the reactor in the inlet concentration is the same as the total moles in the reactor at any time. So I have 1.C in is equal to 1.C. So those are equal. If these are equal and this is 0, then and V in is equal to V out, then I'm left with dCA dt is equal to, well, V in is V out. So I have V in over V times CA in. This is 0, this is 1, and this is the same as V out, or the same as V in and V out. This is V in, so there it is. So I have minus CA plus RA. So in the case of constant density, I just get the standard CSTR equation, where V in over V, remember, this thing is just 1 over tau. And this is, for the constant density unsteady CSTR, I've got dCA dt is 1 over tau, CA in minus C plus RA. If we refer back here, if we just kill the reaction, we get exactly the right answer. I want to give you one other example, which is kind of a neat example, which refers to viruses. I'm going to take 5 more minutes, if that's okay, because I want to get this neat example. Let's assume I have a situation where my species are viruses. So each species is a virus. Now what's a virus? You can think of it as a string of RNA, ribonucleic acid. So a string of RNA is like a word in a language that only has 4 letters. So in English we have 26 letters. So you can think of it as a word where in an alphabet that has only 4 letters. So you can think of each species as another word. So you have words with a bunch of letters. Let's say every word has 100 letters. So you can think of every species as another combination of those 100 letters, another sequence of 100 letters. So you can think of a situation where each RNA wants to make a copy of itself. If it makes a copy of itself, you can think of that reaction as A goes to 2A. But if it makes a mistake, then an A turns into a B, because it turns into a different word. So if we, let C in is 0. So nothing's going in. But since the species themselves are making copies of each other, the system doesn't run out because they're producing copies of themselves. And if I have a situation like that, where A goes to 2A or A goes to B, etc., then I get a bunch of first order reactions. In other words, the rate matrix, the rates are linear combinations of the concentrations. So you can think of that as a matrix A. That's a matrix times the concentration vector. Concentration. And let's just look at what happens to this equation in that case. So I get dCdt, where C is the vector of all the concentrations. So it's the concentration of it's how many of every word I have, every RNA. And that's equal to, well, Vn is 0. Ra is AC. Minus, Vn is 0, so this term's gone. Here I have 1.AC over 1.C times C. Now what's going on here? This equation was originally derived completely differently by Manfred Eisenberg, who's a Nobel Prize winner in chemistry. And he derived it to look at how life started. And I'm not going to go through the details of that. But it applies to viruses, and it's the basis of every antiviral drug in existence today. Let's think of what the rate constant should be. If I have an RNA making copies of itself, then it wants to copy every letter correctly. If I have a word, I want to make a copy, it wants to make every letter correctly. And let's say the probability of copying a letter correctly is Q. So how well you copy each letter is Q. So the probability of copying a letter correctly is Q, and the probability of making a mistake on a letter is 1 minus Q. And from that, you can determine all the rate constants in this matrix A. I know talking about matrices here may not be obvious, so maybe you have to trust me a little bit on this. Something really interesting happens here. What's interesting that happens, I know you heard about this in biology, but you can prove mathematically that at steady state, what you find is the concentration of one of the words, let's say the total concentration is 1. The concentration of one of the words at steady state is 0.999, and the concentration of all the others is really tiny, like less than 0.1. That in biology you call selection, survival of the fittest. And you can prove from this equation that you get survival of the fittest, that the one species wins, one virus strain wins, the Delta variant is winning now, and all the others die out at steady state. But if I plot the concentration of the winning species, the winner, as a function of Q, when Q is 1, I get 100% winner. 100% winner, 0 of anyone else. I copy perfectly. However, as I decrease Q, as I start making mistakes, something really interesting happens. This hardly changes. And then there's a critical value of Q star, where this dropped precipitously. So if the fidelity of copying letters goes down a little bit, nothing changes. You hardly change. The master species, that is the one, the Delta variant, stays the dominant species, takes over. The minute you get, but then it's not gradual. You fall off a cliff once the fidelity of copying crosses a threshold. And this is called the error threshold. Eigen's famous error threshold. Now, if Q is 1, if Q are 1, there's no evolution. Evolution means you have to have little mutations and try them out. So that is actually, and there are some viruses, like for example the poliovirus, where Q is very close to 1. It doesn't change the poliovirus. So the same vaccine that was invented by Sabin, who was a City College graduate in the 1950s, still works today. The virus hasn't changed. And you all get polio vaccines as children. On the other hand, the viruses that change quickly are ones that are very close to the error threshold. So HIV is very hard to come up with a vaccine for because it's constantly evolving. You give it a vaccine and it just mutates because it mutates very easily, but not over the cliff. On the other hand, most viruses aren't quite as agile as HIV. So what does an antiviral drug do? The idea of an antiviral drug, most of them are already mutagens. That is, they make you a little smaller. And the idea is to kick them over the cliff. If you kick it over the cliff, it loses all information and you get all the words. You get garbage. So every RNA vaccine, every antiviral drug today works by making you a little smaller. And the assumption is if the virus is operating close to the error threshold, you kick it over, it's gone. So, it's interesting that this comes right out of this equation, which is a non-constant density CSTR equation. Sorry for going over a little bit. I thought you might like that example.